Welcome everyone back to the SNIFA seminars. Today we're going to hear two talks, one from Anand and one from Martin. Both talks will be about 20 minutes long, and then there'll be time for questions and discussion afterwards. Just the usual Zoom things, so please keep yourself muted during the talks, but feel free to post questions in the chat. And yeah, we're recording the session and it will be available to view on YouTube afterwards. Yeah, so with that, I'd like to introduce Anand. Anand did a master's in computer science and then did some work in industry before doing his PhD on biologically plausible learning rules and meta-learning in spiking neural networks with Wolfgang Maas. And then for the last few years, he's been working as a postdoc in Germany. And yeah, I'll leave him to tell you about his work today.
Thanks, Marcus. Yeah, hi, everyone. Like Marcus said, I'm Anand. I'm a postdoc at Ruhr University Bochum in Germany. I'm part of this institute called Institute for Neural Computation, the group of Lawrence Viscott. And today I'm going to be talking about general purpose event-based architectures for deep learning. So my kind of proposition here is that we need to look beyond biology-based models for deep learning, especially on neuromorphic hardware. So spiking neural networks that we all know and love were developed as models of biological neurons. But I mean, they have become the canonical model for neuromorphic computing, especially for doing deep learning applications. And the focus of neuromorphic devices is shifting further towards deep learning because of their energy efficiency advantages. And with deep learning, you have higher expectations of task performance. So I think we need to ask ourselves, are these biologically inspired spiking neural networks really optimal for deep learning with neuromorphic devices? And what I propose is that we need to design deep learning architectures ab initio for deep learning on neuromorphic devices, because we can distill the essential advantages, properties of these biological models, and we can really customize architectures for specific deep learning, specific neuromorphic hardware. We can design these architectures to achieve exactly what we need in terms of longer memory or better stability properties, gradient properties, and so on. And we don't really need to be beholden to biological models if you're just focusing on the deep learning part, right? So then the obvious question that arises is, what are the key properties of spiking neural networks and what is the desiderata for neuromorphic architecture? So why are spiking neural networks so popular for neuromorphic hardware? So as we all know, neuromorphic hardware is focused on energy efficiency. And there are some properties from biological neural networks and from spiking neural networks that actually lead to this energy efficiency. So one of them is sparsity, both in time and in space. So the sparsity in time is activity sparsity, where activity of the units are transmitted only when needed. So in spiking neural networks, these are the binary spikes that are sent to other units. And then there is parameter sparsity, where you just have fewer connections. Each unit is only connected to a few other units in the network and not all the other units. So activity is really only transmitted to units that need them. So the second main property that has been used a lot in neuromorphic hardware is event-based communication, right? And this is communication that happens only through discrete events sending messages between units. So you're not communicating all the time like you do with a traditional network, but you're only sending like discrete events. And so when you combine this with activity sparsity, units only need to update their state on an incoming event. And in between, depending upon the dynamics that you choose, you don't really need to do anything at all. So there are other properties such as asynchrony, where you don't really have a shared clock signal across the units, and maybe a few others that I've not thought of that spiking neural networks have. So I should say that event-based communication also implicitly implies computing with time. So so that is already a property that's included over here. Okay, so what can we do? So now that we know, or at least we think we know what the properties of spiking neural networks are important, we can think about designing general purpose event-based models. Right? And this is in principle very, very straightforward. All you have to do is add an event generating mechanism to each unit in whatever model you have. And the unit dynamics can be arbitrary. Right? So you could take something that looks like this. So for a leaky integrate fire neuron, or something with an adaptive threshold, or with exponential integrate fire. So all of these standard spiking neural network models, you have an internal state, which is the membrane potential. I mean, here I'm calling it C for reasons that you will see soon. And so the idea is that you have some dynamics, you have some internal state, and then you have this event generating mechanism based on a threshold. And then whenever the event is sent, the state is reset. And there is a recurrence in this within this unit, so that you can really use information over time. So this is kind of like the general principle. So you could quite just as easily use a LSTM or a GRU unit over here instead of leaky integrate and fire dynamics, because you could just add a threshold on the cell state of the GRU or LSTM, right? And over there, the internal state is just the internal state of dynamics. You could also use any other dynamics that you wanted to. So, so what I do now is take this general principle and apply it to one particular example, a gated recurrent unit. And as I go along, I'll tell you why we chose the gated recurrent unit, because it has some very, very interesting properties otherwise as well. But the first thing to do is to kind of look at the dynamics of the gated recurrent unit. This is what it looks like. It has an update gate, which is a gate that's a function of the external input X and the recurrent state Y. And then you have a reset gate, which is also another gate that's with different parameters. That's a function of X and Y. Then you have a proposed update Z. And the output of this gated recurrent unit is some combination of this proposed update Z and the previous time step state Y. Right? So both U and R are values between 0 and 1, and they function as gates as they do in LSTM as well. So because of sigmoid, you always have values between 0 and 1. Okay, so what we want to do now is to use this principle that I described before and just add an event generating mechanism to the GRU. So I write the cell state now as this combination of the proposed update and the cell state, and add a reset to the cell state, and introduce a Heaviside step function with the threshold. So the idea is that whenever the cell state reaches the value of the threshold, it sends the value of the cell state to all the other units. So that is the output of the event-based GRU, or EGRU, as we call it. And the cell state is exactly the same as what we had before over here, but with the addition of a reset mechanism. So every time an event is sent, the cell state is reset, and then it starts integrating input again. So this is kind of what our EGRU looks like. And it's really as simple as that, right? So now each unit is only sending discrete messages whenever the cell state crosses the threshold. And when the cell state is below this threshold, then the output of the unit is 0. So there's nothing being sent at all. And so this very obviously leads to activity sparsity of the network. So how do we do learning? So now that we introduced a Heaviside step function, which is not differentiable, it looks like you can't really do backpropagation through time. But we do know a lot of tricks about how to handle this from the spiking neural network literature. And what we can do is introduce a pseudo derivative or a surrogate gradient for this thresholding function. So, I mean, I show like the particular function that we use. But so what is really cool about this model is that, and this is also true for spiking neural networks, which is that if there is activity sparsity in the forward pass, so if only these white units are activated as you go forward in time, in the backward pass, you get sparsity as well, because you only need to propagate the gradients through the units that are active. Of course, I mean, when you use a pseudo derivative with some support that looks like this, you would have to propagate gradients through all the units that had a cell state between plus or minus epsilon of the threshold. but you don't really need to propagate the gradients through the rest of the units, right? So you can choose an appropriate pseudo-derivative and make the backward pass sparse as well. And beyond the support of the pseudo-derivative, all the gradients are zero, so they're not backpropagated. So, which means that the activity sparsity in the forward pass can translate into efficient backward pass training as well in this model, which is a really cool property that we can use. So this is like the basic model, and we tried this on a bunch of tasks. So deep learning benchmarks, benchmarks that come from spiking neural network literature as well. So the first one we did was this DVS 128 gesture recognition. So DVS, so this is like data that's based on hand gestures collected by this dynamic vision sensor camera in terms of events. So each sample is a stream of events, a stream of off or on events spread out over time. And this describes the movement of the arm. Right? So this is work done by one of my colleagues. And so here's like a table of results. And so the first thing to look at is, so the standard LSTM-based models, so without a convolutional layer in front, achieve about 86% accuracy, and with a convolutional layer in front with the LXNet, achieve about 97.7 or so % accuracy. And so our model can actually quite easily compete with that. So we have a version, so DA over here stands for data augmentation. So it's trained with additional data augmentation as well. So both the state-of-the-art model as well as some of ours. And so our model can easily kind of beat that and get 97.8% accuracy with the CNN and data augmentation, and without, it gets about this, it beats this and gets about 90%. But now what is important is to look at the, not just the number of parameters, but because we are talking about activity sparsity, we want to really have an estimate of how much computation we perform in the forward pass, right? So over here, there's this entire column of activity sparsity, and you see that most of the EGRU models achieve about 80% activity sparsity. And we want a good estimate of how this translates into the amount of computation that's performed. So what we can do is we can calculate the effective multiply accumulate operations that are done in the forward pass. And this takes into account the activity sparsity, because whenever a unit is zero, you just don't do you don't have to do any operation for that unit when you propagate to the next time step. So with the EGRU model, you can really see that we can get very, very efficient models. So for the case without the CNN and data augmentation, we basically are about half the state of the art in terms of computation, but getting comparable accuracy. And for the case with a convolutional neural network, and this is kind of interesting because convolutional neural networks are quite computationally expensive. So this model, for example, has like 600 million effective MAC operations for the forward pass. And we are able to solve the same task with a much smaller convolutional layer and a recurrent EGRU with activity sparsity of 80% and achieve the same level of performance, right? So this is almost an order of magnitude reduction in the amount of MAC operations over here. So if you, and so there is also backward sparsity that is quite significant. So the training is also efficient. And if you look at the activity of the network, it's very reminiscent of what you see with spiking neural networks, which is that most of the units are not active most of the time. And as you go from layer to layer, the activity increases, but you just have like overall a lot of sparsity. Okay, so the second task that we tried on was the sequential MNIST image classification task. So this is one of the tasks where you take an MNIST digit and give input pixel by pixel, scanning from left to right and top to down in the image. And over here, well, I mean, we don't beat the state of the art yet, but we do get really, really efficient models that have comparable performance. So in just sequential MNIST, we have a model that gets 98.3%, but with about like slightly fewer parameters in the state of the art. Permuted sequential MNIST, which is a much harder problem. Again, we get like fewer operations and somewhat close to the state-of-the-art performance. Right? So it basically works well. But so what we did with this sequential MNIST was also look at how the model scales in terms of the size of the network. So in terms of the number of units in the network. And so here is a plot which shows what happens when you do this. On the left side, y-axis, the orange curve is the number of operations. On the right side is the number of epochs that it took to converge to some value of accuracy. And the x-axis is the size of the network. So what is interesting is you see that as you increase the size of the network for the same task, the network converges faster. So this is not quite unexpected, right? This is actually what you would expect to see. And as you increase, maybe it stops converging, but we just ran it up to 2000 units. But the number of operations calculated in terms of these MAC operations stays almost the same, even as you increase the size of the network more than 20 times, right? So close to 20 times. So this is quite interesting because you can actually over-parameterize models and get like better training properties without doing significantly more computation. So, and then the other like really interesting application that we tried this on was language modeling. And so this is one of these tasks. I mean, language modeling is where models really seem to benefit from having really large sizes, as we see in a lot of deep learning today. So we wanted to see how our model performs in comparison, but mostly compared with state-of-the-art recurrent models. So we are still not, recurrent models are still not like close to transformers, but it does get really, really close to the performance of LSTM-based state-of-the-art models. So these are like essentially on the, so I mean, the measure of performance over here is perplexity, so lower is better. So on Pentry Bank, which is a relatively small data set, we're basically able to get perplexity that's close to the state-of-the-art models, but with a fraction of the parameter, a fraction of the computation required, right? And similarly for Wikitext2, which is an even larger data set, again, with about half the amount of computation required, we're able to get quite close to the performance. And I should say here that a lot of the bottleneck of getting good performance, as it is often the case in deep learning, is just the amount of time spent in optimizing the hyperparameters. And so this was a case where we did some hyperparameter tuning based on the computational resources we had, and were still able to get quite close to LSTM-based architectures. So the second caveat over here is GRU models by themselves are not, they have a bit of a slight disadvantage compared to LSTM models. So just like the base GRU model does worse than the LSTM-based models, but we are working on having an event-based version of the LSTM as well currently. So, so the other interesting property that we can see from these language modeling experiments is that you can actually trade off the backward sparsity with the performance that it requires. So you can use this surrogate gradient parameter epsilon. So this is essentially the support of the surrogate gradient. And so the wider you make it, the lower the backward sparsity. And then, but there is kind of like a bit of a trade-off. So as you can see, with some level of backward sparsity, lower than 20%, you get like the best, what looks like the best performance over here, on average at least. And you can kind of make the surrogate gradient narrower and narrower and still have fairly decent performance. Right? So depending upon the resources that you have for training, you could really trade this off. Okay. So, the reason that we chose the GRU for the first kind of model, event-based model, was that they have a very interesting property, which is that the GRU model itself can be written as continuous time equations quite elegantly. So the GRU equations are just, I mean, if you just squint at them a bit, you'll see that they are essentially forward Euler equations of some continuous time model, and you can just write it as a continuous time model directly without much difficulty, right? And so we basically did this to analyze what our event-based model could do. And for this, you essentially take the GRU continuous time model and make it event-based in the same way. So except that now we can really mathematically define things more formally and analyze exactly what sort of properties this model has. So, so we essentially defined all the gates, just like in the discrete time GRU model. We added an activation dynamics, which is essentially a variable that integrates the inputs coming into each unit. This is the continuous time dynamics of the cell state. And this essentially looks very similar to the discrete time equations that we were looking at before. And you can also mathematically more rigorously define the concept of emitting an event. Whenever the cell state of the unit emitting the event reaches the threshold, then the unit cell state is reset to 0, and the other units don't really change their cell state. But all the other units receive an input to their activations based on the cell state of the unit sending the spike. Right? So this is kind of, I mean, I don't want to kind of go too much into detail here, but you essentially end up with like very, very simple equations that describe what emitting the unit means, and you can handle the input in the same way. So what is now interesting about defining the model in this way is that you can also do a backward pass in continuous time based on the adjoint method. So you write the laws using some adjoint variables and the dynamics of this continuous time model. And you end up getting adjoint dynamics, which is essentially like the equivalent of the backward pass for the discrete time model that also look fairly simple. So, I mean, maybe the derivative of the f with respect to c looks like it's going to be a whole matrix, but it's actually just, ends up being a vector. So this entire matrix transpose multiplied by the adjoint variable ends up being just a vector. So all of these dynamics are on a per unit basis. You don't really have to consider interactions between units. And you can calculate the gradient updates for the parameters of the network based only on quantities at the time of the events. Right? And this is a very, very cool and interesting property. So in spiking neural networks, this was kind of called event prop, which is published some time ago. And the same property holds for these kind of general models as well, because as you see, the dynamics of the model is defined quite generally as f. And so what this means is that you only really need to backpropagate. The cross-unit backpropagation communication is also event-based. So you only need to do that at the times of the events. And only within the unit, you need to do some sort of backward pass in between the events. Right? So which can really make training super efficient. Okay, so that's so you can actually look at our archive paper that I linked to before, but I'll link again for more details about this. But this kind of model essentially, I mean, to summarize this talk, biologically plausible spiking neuron dynamics, they are suboptimal for deep learning on neuromorphic hardware. So you can modify the unit dynamics to make it spiking by adding an event generating thresholding function. So, and we define this based on a gated recurrent unit, a GRU. And so what is interesting is that it exhibits high activity sparsity in the forward pass, but it also exhibits sparsity in the backward pass. So in learning, right? So this is true for both the discrete time model, where the sparsity is not exactly the same as the forward sparsity because of the surrogate gradient that we define. But for the continuous time model, the sparsity in the backward pass is exactly the same as the forward pass, and which has the potential to be super efficient. So because we do get the event-based gradient descent updates, and we can analyze it mathematically. So for example, you could really define the dynamics of the units based on stability conditions, based on avoiding vanishing gradient or exploding gradient problems. You could define it based on modeling long-term dependencies, and then still get this kind of event-based updates for such a network. And so you could really have very, very powerful architectures that come out of this. And well, I mean, I would argue that these kind of more general purpose models can potentially replace spiking neural networks for challenging and complex tasks, such as language modeling, but basically like almost a lot of other deep learning applications. All right, so in terms of outlook, I mean, what me and my group are planning to do are explore like other unit dynamics for different use cases, but also really look at which sort of dynamics are good for specific neuromorphic devices. So there are neuromorphic devices which support non-binary packets for communication. We're working on more efficient software implementations of these models. And we're actually working quite closely with TU Dresden in Germany, who developed the Spinnaker 2 hardware to have an implementation of one of these models there and hopefully scale it up to way more parameters and units. So I should say this was joint. So the EGRU was joint work with a bunch of people. So Khalil, Mark, and Christian from TU Dresden, and David from Ruhr University Bochum. And I've linked our archive preprint of this GRU-based, event-based models over here. So thank you very much. I'll take questions now.
Thanks so much. It was a really clear talk and super interesting.
Thank you.
So yeah, I just have one quick question, I guess, and then anyone else can ask away. So I was wondering, so you showed good performance on lots of different types of tasks, but do you think there's a sort of class of task or particular types of tasks that this architecture would really excel at compared to other types of tasks?
I mean, so we have mostly focused on like recurrent architectures, but as far as we have seen anything that LSTM or a GRU can do, our architecture works well for that as well. So it's, I mean, and in principle, you could do the same thing for feed-forward networks as well, right? I mean, the benefits are not as great for a feed-forward network. But yeah, I mean, I don't really see a limitation in terms of the type of tasks.
Okay, cool. Well, yeah, with that, happy for anyone else to ask questions now.
Yes, hey, can you hear me?
Yeah, I can hear you.
Hey, sorry, I had just a little confusion, maybe technical bit, when you talked about the amount of sparsity in the backprop phase compared to that epsilon parameter. And I think I didn't really understand how this relation worked, because in my head, it would have been the other way. The narrower function you would have used, the more sparse you would get as a return, right? I don't really understand how this relation is the other way, or maybe it's just confusion on my side.
No, it is actually what you said. So over here, you can kind of see that. So narrower the surrogate function, the higher the backward sparsity.
Okay, yeah, okay. So sparsity, you mean the less event you get that you need to backpropagate through, right?
Exactly.
Okay, okay. Yeah, my bad. Yeah, I got it. Cool.
I guess the other quick question I had was, you showed at some point a figure with the, oh, sorry, there's a question in the chat as well. Let me just ask this quickly. You showed a figure at some point with the spiking in a few layers. Could you just show that again quickly?
Oh, yeah.
So is it the, so is the top layer, is the top subplot here, is that the first layer in the network? Or is that the input layer? Is that the?
Yeah, that's the input layer. Exactly.
Okay. Oh, so then it is like, so then it is actually a bit different to spiking neural networks, right? Because spiking neural networks, we tend to see more sparsity as we go through the layers. You tend to get more sparse activity in deeper layers. This is kind of the opposite, right? You get more activity in deeper layers.
I mean, we kind of, well, what we found was that this is like really task dependent. Okay. So it depends on like how the input is encoded. So there were cases where if you use like a different input encoding, then you don't really get much sparsity in the initial layers, but then you get more in the final layers. So this kind of varies a lot. There's, but at least like as far as I know, there was no hard and fast rule that we noticed.
Yeah, I mean, yeah, with biology or anything else, I guess I wouldn't want to say a fast rule. I think usually it becomes sparser in deeper layers in spiking networks, but maybe that's not true.
Yeah, that's a very interesting point, I guess. I mean, so in some sense, like these models are really like kind of equivalent to complex neuron models, right? So it would be quite interesting to study this emergence of sparsity and how it correlates with biology.
Yeah. I guess actually maybe Martin later can talk, well, maybe not, but maybe he can talk about how activity changes as deeper layers in the visual processing. Anyway, so there's some questions which I can read out. So Laura Fander asked, hi, thanks for the great talk. Would EGRU be applicable to time series problems like detecting movements with EMG or EEG-like signals?
Yeah, absolutely. So, I mean, anything you can use a recurrent network for, you can use the EGRU, but with the sparsity benefits. So you don't necessarily need to encode your input in terms of events. So if you do, then you would get like an additional advantage, but you could just like for a language modeling, for example, we just use as fairly standard encoding, just like you would do for LSTMs. And then since we're not forced to work with binary communication, like with spiking networks, we can just like pass in a vector of like any real value numbers, right?
Cool. And Colin Will asked, if the paradigm in neuromorphic engineering moves towards the event-based architectures you described and away from spiking neural networks, would that represent a shift away from or towards neural networks that mimic directly the animal brain?
Yeah, that's a very interesting question. So actually, first of all, a lot of the existing neuromorphic architectures already support more general purpose models. So the Intel Loihi already supports what they call graded spikes, which is just sending like non-binary values across. Spinnaker architectures support like arbitrary dynamics. It's just that people have been using spiking neural network dynamics all this time because that's what they were focusing on. But there are of course like analog neuromorphic hardware which have like built-in leaky integrated file dynamics or some other specific dynamics, and this is not something that can be easily changed. So I guess it's already a mix of things. So the question about whether it gets closer or further away from animal brain, I think that's a very interesting question because, like I said, you could really do very similar thing for more complex neuron models. So you could really try to model biology by writing a multi-compartment model with like much more complex dynamics within this framework and try to train them instead of using like point neuron models. Then in that sense, it would actually become closer to animal brain dynamics with all the complexity, right? I mean, of course, it's a separate question whether adding this complexity helps or hinders understanding biology. But you could easily do that. So these are I think like two orthogonal things. It's not really going away from biology necessarily.
Well, thanks for answering those questions. And I think as Martin commented in the chat, that kind of takes us quite nicely into Martin's talk. Yeah, on whether or not different modeling choices take us closer to neural activity. So yeah, okay. Thanks, Anand. And yeah, Martin, if you're here, you could share your screen. Oh yeah, here. You could share your screen, maybe. Cool. And with that, I'll introduce our second speaker, Martin. So like Anand, Martin studied computer science and then did some work in industry. After that, he did a PhD at MIT with Jim DiCarlo. And really excitingly, he's recently been appointed as a professor at EPFL. Yeah, we're really excited to have Martin here today because of his work on brain score, which I hope he'll talk about. And yeah, it's something which has come up in a lot of these seminars, and yeah, it came up just now. So yeah, Martin, thanks.
Cool. Thank you very much for having me. This is exciting. I will try to, I think, mostly talk about brain score. I'll also try to talk a bit about the rationale behind some of the choices we made. And I hope there's, especially with the spiking community, I hope there's going to be some question about what level of abstraction we might want to focus on. As a spoiler, I'll try to put forth a view of spike rates, but hopefully we can have a discussion and maybe you can convince me otherwise. Okay, so I want to preempt this. Yeah, so Mark just said this. I am incoming faculty at EPFL, so if anything that I'm going to talk about sounds exciting to you and you're maybe looking for a position, then please get in touch and let's talk. Also, maybe I can entice you with some pretty pictures. The campus is right by the lake. It's a really beautiful area. Okay, the other thing I wanted to say up front is that everything I'm going to mention here is not just my work. It's really the product of some fantastic collaborations of the people who are shown here. And I've been very fortunate to always have fantastic and smart people to work with. Okay, so up front, just want to declare that the goal broadly of my work and work of the others that I just showed is to model primate visual intelligence. And the plan is for me to first walk you a little bit through what primate visual intelligence means, and then I'll get towards some modeling efforts. And if we have time at the end, maybe we can talk about some more recent models that we recently built. So as a human, if you see an image like this one, you don't take it in all at once, rather you fixate on different areas of the image. So for instance, you might first look at the stroller, you might then also look at the bike, and you might notice the dog sitting on the beach here. What's really fascinating about humans is that you can detect these objects in foveated parts of the image in a very brief amount of time. So I hope this works over soon, but I'm gonna flash these images in brief succession, and I bet you will still be able to recognize all of the objects pretty seamlessly. So these are around 100 milliseconds or so, and probably you have no trouble recognizing what the objects are, even if they're blurry and if they're really fast. So this is a paradigm that we call core object recognition. So it's the image at the center of phobia, usually presented very briefly. And like I said, humans are really good at this. So we can easily recognize this image as a dog. We can even do this when there are changes in size, color distortions, occlusion, or motion blur. It's still going to be really easy for you to recognize the dog in all of these images. And while we know what the area, or what one area is that enables this behavior, this area is called the ventral visual stream. I'll talk a little bit about that later. We don't know how exactly this works. So we know where it roughly happens that we are able to good at object recognition, but we don't really know why. So the one big question in the field of neuroscience has always been, how exactly does this work? And turns out, if you look at this a bit more closely, so on the right here is a diagram of all the visual areas that are thought to be involved in vision. This is classic work from Feldman and Nelson. And the point I really just want to make with this slide is that brain processing is highly complex. So it has just been very difficult for our field to make sense of what exactly is going on. And so quite necessarily, our field had to start with what I'm going to call piecewise efforts. So for instance, if you're interested in vision, you might stick some electrodes in a primate brain, maybe in the early parts of the brain. You might collect some data, maybe even build a model that explains that data. And then there's another group that also collects some data, and maybe they also build a model. But eventually, what our field until recently was left with was this collection of isolated data and isolated models. So we had a lot of the pieces, but nobody really talked to each other in my mind. This is somewhat anecdotal to the story of different men feeling an elephant and nobody quite getting the full picture. So I don't want to diminish any of this work. It's totally necessary. But I think everyone would agree that if we're after a unified model, then these steps alone are insufficient. So what I'm going to try to advocate for is that our field builds what I'm going to call system models. And the idea to get there, I think it's not a clever idea, it's just a necessity, is integrative benchmarking. And this really just means let's take all the data together and use them collectively to guide and constrain the models. And that is exactly what BrainScore is trying to enable. Excuse me. So coming back to the anecdote, our hope is that this will let us see the full picture, not just isolated parts of the elephant, but the full elephant of primate vision. And so zooming back into how exactly the ventral visual stream processes objects. So when light hits the retina, so an image is processed by your brain, it sends it through LGN to V1, which is the first cortical area in the primate brain to process images. It then goes through a hierarchy of stages that we call V2, V4, and IT. And IT is thought to hold the representations out of which you can linearly decode things like object identity, maybe also size or rotation or different things like that. So when we now want to compare models to these mechanisms in the brain, then there's really two major sets of data that we've been working with. One is the behavioral data, so the outputs of the system, and second is the neural data, so how does the system internally represent these incoming images. And so these together make up the benchmarks that we now have in BrainScore. And I'm going to walk you a little bit through what exactly those are like. So I'm going to show you one behavioral benchmark, and you can play subject for a little bit to see what the data collection is like. So imagine you're being paid for this. So you have to fix it on the white dot. And I'm gonna flash an image, and then there's gonna be two choices. So in person, I would ask you to raise your hand, but maybe you can raise it on Zoom even if your camera's off. Okay. Maybe you can just think which choice you would make. Okay, ready? Oh, all right. So you would probably have chosen the dog, in which case, as a subject, you would be getting paid. And this was a pretty easy trial, but you can probably imagine if these images are rotated in some ways and we introduce changes in viewpoint parameters, at some point this gets pretty tricky. So for instance, here we might not have been sure if this was really a bear or maybe it was a rhino or something else. So what we can do with these trials is we can build a confusion matrix that tells us for every image and all possible distractors, how easy is it to recognize the correct object in the image. So for instance, recognizing dog versus fork is pretty simple. So it's indicated in green and blue colors here, whereas maybe distinguishing the bear from the rhino might be more difficult, which is then indicated in red. So when we then build a benchmark, this is the behavioral data that we work with from the humans. And the experimental paradigm to show the models is to just use the same images. We use a unified API to work with all the models. I'm not going to go into detail on that, but it's just a way to treat all models as the same thing. So here we have the models perform a task of object categorization and have them look at the stimuli that were also shown to the humans. This then allows us to get the behavioral predictions of the model. So these are just the choices that the models make on these images, whether they got confused in certain ways. So we build the same kind of confusion matrix. And then we use a similarity metric that here is simply a correlation to compute a score of how aligned the models and humans are with respect to this particular task. I want to point out that this is not just accuracy, but rather it's really the image level alignment. So if humans get certain images wrong, then the model is actually being punished if it gets it right. So the model has to make the same mistakes as humans and has to get the same things right. It's really alignment, not just ground truth accuracy. Okay, so the nice thing about this task setup is that we can also run it on monkeys. Here you can see a macaque monkey in its home cage doing the same kind of task. So at the bottom here, you see a screen, should ring a bell, is the same kind of task that you just did. And it gets a reward and a green screen if it gets it right, and a black screen and timeout where it usually wants to keep going if it gets it wrong. And macaque monkeys are extremely good at this. And I should say that it's been found in the past that their visual system is extremely similar to that of humans. But in the case of monkeys, we can use more invasive tools. So we can show images and record from their brain activity at the same time. So here we record the spike rates. And essentially, you can think of that as one vector across neurons per image. So at the end of the day, we're left with a matrix of images times neurons, where essentially one element tells us how active a particular neuron is for a particular image. And I want to take a brief moment to give some rationale for why we're choosing spike rates here. So this is work by Mashaj and Hong in 2015. And these plots here are different sites from the recordings that I just showed you. The x-axis is time. So 0 is stimulus onset. The stimulus is on for 100 milliseconds. And then for many sites, you get the typical spike responses. Now, we usually choose to use the spike rates between 70 and 170 milliseconds. That's where the neuron is most active. We don't use the spikes, but rather how many spikes were within the time period. And that gives us pretty much the matrix that we just saw. And the reason we do that is because it was found that when you fit a linear decoder on the spike rates to predict object classes in the image, then you can actually predict human behavior extremely accurately. So the plot on the right, to explain a bit more, on the x-axis is performance. So this is just ground truth accuracy. And the y-axis is consistency with human behavior. So again, how similar are the choices of IT to humans? It's a similar metric to what I showed you before. So do you make the same mistakes to get the same things right? And for instance, in V4, we don't get this alignment, even though we extrapolated, we get really good performance. But in IT, from IT spike rates, we get high performance and are sort of in the human zone. So we are consistent with human behavior. i.e. we make the same mistakes and we get the same things right. And because we found that spike rates are the thing that actually predicts human behavior, at least in this task, pretty much perfectly, we so far didn't see a reason to go down to spikes. But maybe this is something for the discussion where we can talk more. I'd love to hear other viewpoints on this. But really, this is to say we're using spike rates, and all the rest of the benchmarks are going to be on spike rates, typically in this 70 to 170 millisecond window. So again, when we build a benchmark now to test the models, we show the same images to the model. We're going to have the model look at the images. I should say, since there's many layers in the model, we typically pre-declare some of the layers to be different areas in the ventral stream. So maybe this layer is V1, this one is V2, V4, and IT. We usually do this on hell data, but I'm going to leave it there. So we record from the corresponding area, which has been pre-committed to a certain layer in the neural network. And then we get the activity, so the activations in the of that layer in response to the same images that the monkey was shown. And then we use a similarity metric that's called neuropredictivity to obtain a similarity score. And again, this assesses the internal alignment of model and parameter representations. If there are questions, I can talk a little bit about what the neuropredictivity measure is, but in a nutshell, it's really, we fit a linear regression from a subset of the model predictions to the data. So we cross-validate over images. And then on held images, we apply that regression, so the regression weights, and try to predict the data. And then we compute a correlation, do this tenfold, and overall get an overall similarity score. There's different ways of doing this. There's also ways to compute a similarity score without regression, for instance, RDMs, for those of you might have heard of that. But yeah, so there's different options. We typically use what we call neuropredictivity, or this regression measure. All right, so putting it all together now, we have the brain. We get measures from the brain in the visual ventral stream areas ranging from V1 through IT, as well as the behavioral outputs. These then make up the benchmarks that we test models on in BrainScore. And for model candidates, we pre-commit certain layers or single layers to the regions in the parameter stream. So when we actually run models, I'm going to show scores on the different subregions on the left. We can test, for instance, HMAX, which is a more classic neuroscience model. This is from, I think, the 1999 or so. It performs okay, but maybe that's a lot to wish for. So when we now tested the latest, at the time at least, latest deep learning models, including like ResNets, DenseNets, MobileNets, and whatnot, we find that one, they're a lot better than what we had in neuroscience before. So certain of these networks at the time were the state-of-the-art models of neural and behavioral alignment with respect to primate vision, but also that they have some ways to go. I want to point out that all of these scores are always shown in an up-to-date fashion on the BrainScore website. So I encourage you to check that out. And again, here, the models are all compared in a unified manner and not just on one benchmark. So coming back to what I said at the beginning, we don't want to just see a part of the elephant, but rather we test models on all the available benchmarks. So ideally, like, the models attempt to predict all past, present, and future data that we have available. And then our community is adding more and more of these benchmarks. So I really think this is a way to guard against overfitting, because models have to predict data that maybe doesn't even exist yet, but that someone is going to collect in the future. And it's a much stronger test of generalization in my mind. And to share what this looks like right now, so at this point in time, we have 51 different neural and behavioral benchmarks. So these range from distributional measures like center surround modulation in V1 up to behavioral generalization for behavior, as well as everything in between. So I really think this is quite an extensive set now. And at least to my knowledge, the biggest set of primate vision benchmarks that are publicly available. Now, we can also do some science with this. So on the y-axis, I'm going to plot average brain score. So this is going to be the average over V1, V2, V4 IT neural, as well as the behavioral measures that we have. And so one dot is going to be one model. Across all the models, we found, at least in 2018, that models from the DenseNet and ResNet families were the most brain-like. You might notice that these happen to be models that have skip connections. So there might be some architectural insight there as well. But what we can also do with this now is we can ask, is there some kind of normative variable that explains why some models are better than others? So can we find something that predicts the brain score of a model? And there are two goals for this at the moment. One is it might hint at how the brain optimizes. So it might tell us why some models are better than others. And the second goal is just an engineering goal, which is that if the x-axis is easier to optimize than the y-axis, then that's a way to more efficiently improve the models. And so what we found is that plotting ImageNet top 1 performance versus brain score actually gives us a pretty strong correlation. So the better models are at ImageNet, the more brain-like they are. And ImageNet, I should say, probably everyone knows this, but it's a big computer vision classification data set. So over 1 million images, and the task for models is to classify the objects in the image. And so at the time we thought, oh, great, maybe we can just wait for ImageNet to, or for computer vision to solve the brain for us. If this correlation holds, then maybe we can just sort of sit back and eventually computer vision will have a perfect ImageNet model that maybe is also a really good model of the brain. But you might notice that even for these models, there's still a long way to go. So we're far from done. And maybe to calm the enthusiasm around this a little bit, we found this year then that if you look at the latest models, there's actually no more correlation, or maybe even an anti-correlation. So models that are better than ImageNet now are no longer better at brain alignment. Okay, so I want to spend maybe the last couple of minutes to talk about some models that we've built. I'm going to go over this pretty briefly. If there are particular questions on one specific model, then let's just talk about them in the discussion. So like I said, the models are far from perfect. And I think some people take this to mean, oh, maybe deep learning is inherently flawed. For me, this just means there's room for improvement. So I think the dogma of neural networks is consistent with the neuroscience dogma. So I think staying within that framework makes sense to me, but clearly there's work to be done. And we need to make the models better because so far they're poor in many ways. One way in which we've made models better is a model that we call CoreNet. So typically these deep neural networks have hundreds of layers, which is a bit difficult to align with neuroanatomy. So what we aimed for in CoreNet was to build a much more compact model that only has about a dozen layers. And then in order to retain performance, we introduced recurrence. So this is one block of CoreNet. It has 4 blocks that correspond to V1, V2, V4, and IT. And you notice that the block has this recurrent motif. So input is processed, but then it's processed again with the same weights. So it's a simple form of recurrence that is not stateful in this case, where it only has a very simple state, but it actually gets us pretty far. I don't know if this plot here, but with respect to other models, CoreNet is much, much more shallow, so many fewer layers, but retains image performance as well as brain score performance, and maybe even generalizes a bit better. One other point that we were really excited about with this model is that it allows us to test if we can predict temporal dynamics, so the spike rates of IT over time, and turns out that it can. So the y-axis here is how long it takes the IT representation to solve an object, meaning that if you, at different points in time, if you try to use this decode approach that I showed you before, and you try to decode the object, at what time does it actually recognize the object? So some objects or some images are recognized earlier, some are decoded later. And turns out that CoreNet can, to a first extent at least, predict when exactly that is going to happen in the IT population. So this is one measure of temporal dynamics in IT. Another model that I recently built is called V1Net. So here we found that if we plot the brain score V1 alignment of models versus the robustness to white box adversarial attacks, then models that are more like V1 are actually more robust. So for instance, the red dots here are models that are adversarially trained to be robust to corruptions in the image. And so my colleagues Joe Lopello and Tiago Marx built a model that uses a V1 front end that is not trained. It's really a classic V1 model from neuroscience in a sense, and that is put in the front of a network, and then the rest of the network is trained end-to-end on ImageNet as usual. And that network is almost by design better at V1, but also happens to be much more robust to these other sort of attacks as well as image corruptions, and without any regulatory training. So this is just standard training. So for some time this was I think state of the art on robustness. Now it's probably been superseded, but it's really maybe a sign of neuroscience giving some insight into machine learning again. And so the final thread I want to mention here is that there's usually a lot of controversy around the training of these models. So usually they're trained for millions of images and for many epochs. So in this work, we showed that you can actually get away with much fewer updates, meaning that on the x-axis here is the number of epochs times the number of images and also including the weights. And we showed that actually without any training, you can already do decently well on brain score. So at least with respect to some standard model, and then with 2 orders of magnitude fewer updates, you can already retain around 80% of the score. So far from perfect, but I think a pretty decent first approach that shows that maybe you don't need all that training. There's a paper came out today from Iqbal Hosseini in F. Ranker's group that showed similar results for language. So this might be somewhat consistent that maybe we don't need all the training to be brain aligned, perhaps at least for the neural areas. For behavior, maybe we need other downstream training, but it seems like at least for neural alignment, we don't need as many supervised updates. In fact, at Vision, my colleague Cheng-Su Tsang found that you can use unsupervised methods, and without any training or without any labeled images at all, you can already do decently well, at least on smaller architectures. This has yet to be generalized to larger models, but I think this gives some hope that you can relax supervised training to a good extent. Yeah, I'm gonna leave the models there. Let's talk more about it in the discussion if we have time, and wrap up. So most of what I talked about was this platform BrainScore, which is a set of integrative benchmarks that allow us to identify the current most brain-like models in vision, and also discover the key relationships between neural function and computation. I showed you one example of that, where we show that ImageNet is a strong predictor of BrainScore, at least up to a certain level. And then second, I told you that the models still have many flaws, but I think that also gives us a reason to improve them and just build better models. And I showed some examples where we improved the neuroanatomy and their training. So with that, again, please reach out if you're interested in these questions, and let's talk about the questions now. Thank you.
Cool. Thanks so much for that talk. It was so interesting to hear. So yeah, I'll start by reading a question from the chat and then open up the floor. So Mark Schoen asked, thanks for the interesting talk, Martin. How do you measure spike rate for feed-forward ReLU networks? And then he has another question, but I'll ask that.
Thanks for pausing. I can never keep track of the question.
Okay, sure. That's the first question.
So the spike rate is really just the activations of a particular layer. So let's say you have a 10-layer network, then maybe you declare layer 5 to be the one that best corresponds to V2 or so. And then when you show images, you just keep track of the activations. So these are continuous networks. So there's some real valued number there. And we can treat that as a spike rate. Like I said, there's 10 ways to compare them. We typically use this linear regression, which then allows for like a linear rotation and rescaling. But that then aligns it maybe more strongly to the actual spike rates from the brain recordings. But really, it's just the activations in the models.
I think that, thanks. And then Mark also asked, recently transformers have moved up the ranks on ImageNet. Is the recent trend in correlation observed due to the trade-off between convolutional neural networks and transformers? And do you find transformers to be less brain-like?
Yeah, that's a really interesting question. I don't think I have a definite answer. So I have maybe some pieces of an answer. So some of the recent trend is indeed because transformers are better at ImageNet, but a lot of the transformers we tried really sort of went down the hill on BrainScore. So initially we thought, oh, maybe transformers are just the wrong architecture. But then earlier this year, we had our inaugural BrainScore competition. So people were submitting models and tried to predict a lot of these benchmarks. And the, I think, second best model in that competition was actually based on a transformer. And that's now like, I think, around top 3 on the leaderboard. So I think it's, at least to me, it's not clear if there's really a trade-off with the architecture and if maybe transformers are a less brain-like architecture, or maybe architecture doesn't matter at all. Like, I guess that's some of the intuition in machining right now, that at least if you're using a reasonable space of architectures, then as long as you scale it up big enough, maybe it's just not as important. I'm not entirely sure from the brain side. It seems like some transform architectures are not great, at least with respect to certain kinds of training, but then there also seem to be ways to remedy that and actually make it pretty well aligned on these benchmarks.
Yeah, thanks. And then, yeah, we have a question from Roy. Roy says, what do you think about interpreting activations as voltages instead of firing rates? Like C. elegans neurons, is it presumptuous to assume spiking?
Yeah, there's probably a deeper discussion here. Maybe so I come more from an engineering background. So maybe my somewhat provocative answer is it seems to work, so I'm so far okay with it. I think we, as a neuroscience community, we have work to do to make it more aligned. That's what these models are trying to do in some ways. We haven't really worked on models that really output activations that could actually be voltages. I think there are other groups that have done some of this, where you also respect the balance of, for instance, excitatory and inhibitory neurons in the brain. The models I've shown you so far do not do that. They might stumble upon inhibition by accident, but we certainly haven't enforced it. And probably without the regression, if you just view these activations, I would guess, I know they don't immediately look like spike rates. So they're like in a linear subspace, they are aligned, but maybe not per se. And I should say that the reason for this linear alignment is really that if you compare two brains, so for instance, two monkey brains, you also just can't find like one neuron here that corresponds to the other one there. Really, you always have to allow for some linear rotation in these higher level visual areas. So I think the linear regression is a fair thing to do. Maybe there's ways to make it more restrictive. But yeah, I think there's ways to go on the models on that front, yes.
Yeah, I also just wanted to add, so I really love the approach. I remember when the first papers came out, and I think there's loads we can learn from it, but I guess just as it's like a devil's advocate question. What do you think we could learn from a model which had a higher brain score? So I think is 1 the top brain score we could get up to? So like, what would a model with a brain score of 1 tell us?
Yeah. So yeah, 1 is indeed the top value. Like we normalize all the scores by an estimated ceiling. So how consistent and reliable is the data? So you don't have to predict data that maybe the data itself can't predict. That's one version of the ceiling. Yeah. So what would it mean to have a perfect model? So I personally am most excited by sort of the engineering aspects of it, or the application aspect. So the Color Lab recently had some papers where you can use these models now to, for instance, control the neural activity. So let's say you have a good model of IT that can predict IT firing rates from images. Now you can sort of flip the whole thing around. You can ask, what do I have to do in order to drive some of the neurons really high and maybe keep everything else really low? So let's say I want some one hot encoding in the neural space, and I want to really drive one IT neuron up. Then what are the images that I have to show for this? And you can, there's different techniques for this, but one of them is you can backpropagate through the entire network onto the pixels. So you can change the pixels in a way to maximally, at least predicted by the model, maximally drive the IT neuron. And that actually works. So you can actually use the models to control neural activity in that way, sort of non-invasively from stimuli alone. And so this was by Bashaman and Carr in Science 2019. And one thing that's somewhere in the appendix that maybe we should talk about more is that we looked a little bit at the alignment on brain score measures versus how well the models can control neural activity. And turns out there's a pretty strong correlation. So the more aligned models are at some of these measures on brain score, the better they're able to control neural activity. And I think that's, in my mind, that's a general trend. Like I think if you can predict something, there is a lot of hope to be able to control it and maybe to do other cool things with it. So I think if we have better and better models, then in my mind, there's a lot of hope to maybe even one day go towards clinical applications. There's actually one key thing I want to focus on in the lab I'm going to set up to try and see how far we can go with these models. What can we really do with models that are pretty predictive, and maybe what are the key shortcomings that we need to focus on? Because like I said, there's a ton of ways in which they're wrong, and I'd love to get a better handle on what exactly would be the most impactful to fix.
That was a great answer. So just, yeah, so I guess just to follow up on the last bit of it. So you would imagine that if you had recordings from like a disease model, and then you could build models which had a high brain score on those disease model data, then what you'd compare is you'd compare the models, the models between the standard data and the disease model data and ask what's different. And maybe that gives you some intuition or hypothesis to test on what's going wrong in the disease model.
Yeah, exactly. So one concrete project that we're direction in the space that I've been working on is sort of towards visual prosthetics. So let's say if you have a model that can predict what the behavioral effects are of microstimulation applied in IT, then you might be able to use that model to infer the right stimulation patterns to elicit particular visual percepts. And yes, like this is unpublished, but it looks like there's some hope that this works. At least quantitatively, the model predicts this pretty well, actually. So for instance, you can predict that depending on which sites you stimulate, you're going to get more of a face response or less of a face response from a monkey. And so I think like long term, if we then improve on this axis, then we might be able to get models that one day can help people that are blind and maybe can actually have a visual prosthesis that stimulates and recreates some of the biomimetic vision. And I think that we need the models in here because we don't know how to stimulate right in IT. The models might be able to tell us what exactly to do.
Oh, that sounds really cool. And yeah, I mean, I guess sort of following up a bit on my question about getting to the brain score of 1. Again, I'm not sure I believe it, but I think I just have to say it as the snooper host. Do we think that using networks with leaky integrate and fire neurons that's the missing 0.6 brain score? Is that all we need to do to get the brain score up to 1?
I don't know. I would love if someone tried it. I think like so far we don't have a single model submission that is a spiking neural network, and I would love if we just had some of those models up there. I don't know, maybe Anand, if your model is applicable, I would love if someone could submit it.
Yeah, I was actually thinking of exactly the same thing, but that's
awesome.
Yeah, that's quite doable. It'll be quite interesting to see how well it does with the brain score.
Yeah, that'd be awesome. We have a bunch of tutorials to help with the submission, and we can always get in touch, and we're happy to help more.
Yeah, awesome.
Yeah, I mean, I guess it doesn't even have to be spiking. We can see, well, yeah, following up the question earlier, we can compare the EGRU network to the spiking network, for example.
Yeah, anything that can make neural predictions, like so far on the level of spike rates, is fair game.
Cool. Cool. I have so many questions, but I feel like I could just keep asking all day. So I think I'll leave it. Well, maybe just one last one. So I remember when the first paper came out, the idea was to have, maybe I'm wrong, but wasn't the idea to have like data from other model animals as well? Or are there benchmarks for other animals yet, or not really?
So far, no. We've been talking to the Allen Institute a little bit. I think there are some like different threads in the mouse community that may be interested in this. I think so far it's unclear to me if we have found someone who really wants to spearhead this. Like I don't know anything about mice, so someone else I think would have to lead this. We're also working on making the whole platform or the whole code library more modular. So for instance, currently we're working on a brain score for the human language system. And I think, from there, it should be easy to adapt it. So like all of this is open source. We have support. So we definitely want to grow this in some ways. I think it's just really up to the sub-communities to figure out if they want to do this, if the time is right for them. For brain score vision, I really hope we can get some more human neural data on there as well. Like right now we have a lot of human behavior data, but like no fMRI recordings from humans, for instance. So yeah, definitely plans to expand beyond what we have right now.
That sounds great. Yeah, well, unless anyone else has any more questions, I think that I'll say thanks so much to both of our speakers for the time. And thanks to everyone for all the questions and interesting discussion.